Today I will be talking about the composite construction of recurve bow limbs for use in competitive archery. So a bit of background, recurve archery is one of the Olympic sports, and for this we use recurve bows that have a central riser portion as well as a limb on the top and bottom that are used as the energy storage and for energy storage and transmitting the energy to the arrow. So because this is an Olympic sport, there's a lot of competition at the top, which means that there is a lot of drive for improving the equipment, and as this goes on, these advancements trickle down towards the average consumer and user of bow equipment. So like I said, bow limbs store the energy of the shot. They flex backwards when the archer is at full draw, and then as they flex forward, they impart energy onto the arrow and fling it downrange. Because of this, they need to have flexibility, but they also need to have high strength, and especially for archery, you need to be very consistent. Archery is a sport about hitting the same target every time, and so consistency is very key. Within bow limbs, both carbon and glass fibers can be used. In general, glass fibers are used in lower cost and lower quality limbs, such as this WNS Explorer 1 shown here. This limb has a cost of about $80, or a set of these limbs is about $80, and this is pretty typical construction. There's a wooden core with a layer of fiberglass on each side, so the wooden core provides the flexibility while the fiberglass provides the strength. On the higher end, there are limbs such as the Hoyt Axia, which are carbon fiber limbs. A pair of these limbs is about $800, and they are made with carbon fiber with a wooden core, although some carbon fiber limbs are purely carbon fiber composite. This set has a wooden core and then the carbon fiber on either side. Here's another close-up look at the Hoyt Axia. So as you can see, there are several layers. This thin layer at the bottom is made up of 8 layers of carbon fiber composite. Then there is a few wooden layers, shown here, 2 brown and 1 black, and another 8 layers of carbon fiber composite on the front of the limb. This system is made with the same resin soaked throughout the entire system. This helps binding the layers together and adding extra strength. The wood varies in thickness to account for the asymmetry of the forces that are being placed on the limb during the shot cycle. At the base, where it attaches to the riser, it is much thicker, and then tapers out as it reaches the end of the limb. Because this is a relatively low volume part as a high-end piece of equipment, it is most likely made using a hand layup of the carbon fiber layers on either side of the wooden riser. Because it's a hand layup, there needs to be some way of drawing the pressure down to force the layers together. I'm speculating that they are using an autoclave for this process. A vacuum bag to seal the part, combined with the pressure inside the autoclave as it's curing, will help force the layers together and eliminate any voids in the system. Eliminating the voids is key for providing strength and stability to the limbs. They are designed for tens of thousands of shot cycles, which means they need to be very stable and not have any cracks that may form or grow, or voids that may grow in the part. Within the autoclave, the heat would then cure the resin and produce the final part. Stress testing on these limbs are done to ensure their consistency for archers. Number one is in their minds is the dry fire durability test. What a dry fire is when an arrow or a bow is drawn without an arrow and released without an arrow on the bow. What this does is all of the energy stored within the limbs at full draw is then released back into the limbs. This causes very high stresses in the limbs and can result in limb failure if they are not properly addressed and accounted for. Again, dry fire is a situation that should never be done on a recurve bow, but Hoyt does test this exact scenario to ensure that in case of accidents, the limbs are able to function just as well afterwards. Additionally, they test for rotational stability. This is a very long part held at 2 points and its ends, and so torsional stability, or twisting around the main axis, is very important. If there's any twisting, that can affect the shot stability and shot consistency, and so there is a big desire to make sure this is as consistent as possible.